Yeah, okay. Let's continue. So, what was that? That was negative 574 kilojoules. Yeah, so wait, what are we multiplying the first equation by? What did we multiply the first equation by? By 2, okay. So we're multiplying by 2. So then, that means we're going to have 2h2 plus 2s, giving you 2h2s. And does that change my delta H value at all? Yes, you have to multiply by 2. So what do I get? Yep, negative 41.2. Yeah. So we didn't flip it, so the sign stays the same. Okay, so now it's a little bit of a trick because now the last one, the last equation, it does nothing appears in our final equation. So that means everything will needs to be canceled out. So what I do is I cancel what I have existingly already before I go and figure out what if I need to multiply it or flip it or anything. So I look at the equations I have right now and I see if there's anything on both sides that appears. So I see that O2 can cancel with the O2 on the right side, right? So I know I probably could have lined up my arrows a little bit better, but you can see the arrows goes like that, right? So O2, anything else I can cancel? Anything else I can cancel on both sides? SO2, I don't see an SO2 that can be canceled. Because I only see SO2 on the right side. I don't see any SO2 on the left. I haven't transferred my third equation over yet. Don't ignore the third equation. Yeah, I'm just looking at the transform stuff on the right side here. So how about 2h2 with the 2h2 right here? Yeah. So that's a good one, and I believe that is it. Okay. So if I look at these equations, these smaller equations, are there anything I need to get rid of that should not be included in my final equation? Oxygen, so that's a good stuff. Well, oxygen's already been canceled out though. I don't have any more oxygens. That's what I'm saying. I haven't inputted my third line onto my, right? I haven't written anything here yet, right? I don't know. Maybe I need to flip it, right? I don't know what I need to do. But right now, what I have on my equation number 1, equation number 2, and 4, what is found there that is not on the main equation? Yeah, sulfur. That's what I was looking at too. So that's sulfur. Wait, are you sure that's not a S2? Or is that a S or anything? Okay, okay, okay. As long as you copied them correctly, because I do see a S and S2, and I'm not sure if you can cancel that because, like, are you sure you wrote the first and third equation correctly? One of them is S and one of them is a S2. Yeah? Okay, alright. Hmm. Well, let's just put it in. So looking, just don't worry about the balancing right now. Just look at the third equation, right? If you look at the third equation, you have SO2 going to O2 plus S2, right? Here, if you just put that in as is, because you said we want to get rid of those two S's. And here I do have two S's on the product already that I can cancel with. So if I just put it in exactly the way it is. Oh, I see what you mean with the balancing. Yeah, we should definitely balance that, or else we have an extra oxygen there. Okay, so how should we balance it? Uh, God. 1, 3, 1, 2 for which equation? The fourth one? Yeah, 1, 3, 1, 2. All right. Okay, because that's gonna, yeah. So let's make sure we go change it back on the modified equation, right? So we need 3 here, 1 here, 2 here. So let's erase that O2 cross mark because I'm not sure how we should cancel it now until we write more things down. What about the equation number 3? The equation number 3 is good. And yeah, everything else is good now, right? Okay, everything else is good now. So still looking at the sulfur. Oh, yeah, still looking at the sulfur. Wait, did you erase that 2 on the S? Oh, so there was no S. Oh, there was no 2, I mean. Yeah. So that makes sense now. So what do you think we need to do to the third equation then? Multiply it by 2, exactly. Because if we multiply it by 2, that's how we're going to get those 2 S's there. Yeah. So we have 2 SO2, and that's going to turn into 2O2 plus 2S. And then again, make sure your delta H value is going to be multiplied a bit. And 297, we basically have 594. And these are all in kilojoules. Because just be careful, sometimes they might not be in the exact same unit. Then just make sure they are all in the same unit, right? Okay, so now if we look at this makes sense. 3 oxygen on the left side is going to cancel with the 3 oxygen on the right because you got 1 on the equation number 2, you got 2 in equation number 3, so they add up to be 3 oxygen. I know I crossed this. Some teacher make you like write down all the reactants together into one single one and then all the products in the all single one and then cancel. But what's the point of that, right? We can cancel it off of here right away, right? Make sense? Yeah, okay, so what else can cancel? So the 2S with the 2S. And then if you did this correctly, you should only have the products and reactants that you want. So if we verify what's left over, we have 1 of the CS2. We got 2 of the sulfur dioxide. Oh yeah. Wait. Yeah. Wait. Yeah. Sorry. What was the actual thing it was H2O. That's why. Yeah. So we forgot to cancel that one. It was the H2O. Oh yeah, I didn't see the H2O because I just remember there were 2 things on there. Yeah. So we got the water. We got the SCS2, and then on the product side, what else do we have? We have the 1 of those CO2s, and then we have 2 of those H2S's, right? And then now the final step, the actual thing they want, is the final delta H. So it's final delta H, you can find that basically by adding up all your modified delta H values. Okay, so now we're going to add all of them up. We're going to go negative 41.2, negative 242, 594, and negative 574. Right, and let me know when you get a value. Multiply. Oh, we didn't multiply that one? Oh, damn. Times negative 2, right? Oh, yeah. So what should that one be? Yep. So negative 484, right? Because we multiplied by negative 2. Okay, so if that is the case, I need to go and minus another 242. My Zyboard is lagging pretty hard right now. Sorry? Do I have another one? Yeah, yeah. So do you want to do the second type or you want to do the same type? Okay, let's do a same type. Um, law. Let's see. Yeah, I'll probably give you a whole worksheet. She didn't give you enough practices, right? Oh, just one. Okay. Yeah. Yeah, this one is more complicated because most Hess's law questions like this would usually have 3 questions or even 4. So here I am going to... Alright, so I am putting this link here so you can get onto the PDF. What you're gonna do is to access this, so you can copy paste this. You're gonna long click, use your pen tool, long click that link, and it should bring up the Word box. And you just need to copy it and put it in. Anyways, so you can use those practices, but I'm actually just gonna pick one right now. I'm gonna pick maybe the last one. I'll pick problem number 5, but then I give you that link so you can use that as practice with problem number 1 through 4. Say that again. Oh, use the pen tool and does it not work? Long click it. Yeah, yeah. Yeah. I'll probably put it in a Zoom chat instead. There. I'll put it on the Zoom chat right here. Alright, there we go. Holy crap, is that even a right link? That's not the right link. Give me 1 second. Alright, there we go. This is the right link. Alright, but anyways, you can look through that after, but I've already pasted the question I want us to do. It says use the following equations to calculate a delta H for the following reaction. Okay, so I'm gonna let you take the lead then. Yeah, so you saw my setup. I mean, you can set it up differently as well. Some people go like, oh, I multiplied this, and then you write the ones down here. Some people do a side by side. It's up to you. Actually, that was my first time doing side by side. I usually just do it down here and be like 1. I go like 1 times, you know, whatever it is that I'm multiplying. Let's say -2 or something. And then I'll write the equation, and then I'll write the H. Because what I want to do is I want to make sure, no matter how I set it up, the important thing is I want to be able to line up the modified equations so I can try to cancel them. Yeah. Uh, 3 multiplied by half, and why did you do that? Because of the H2? Yeah, perfect. Oh, because of the C2H6. Oh, sorry, I thought that was equation number 1. Yep, exactly. So that's what I always go to. I go to the things that are only found once within the elementary steps. And actually, luckily, this question only has, like, everything in the main equation is only found once. But that's not always going to be the case. Yeah, so I would put the delta H value beside them as well. Yeah, exactly. Wait, you multiply by half, no? The third equation. I keep looking at the first equation because first equation you multiply by half also. Actually negative half, but yep, that looks good to me. Yep. Yep. So yeah, now make sure you cancel. Just verify that you have the actual equation that you want. And this one was a little bit easier just because the elementary step equation has been balanced for you. Yeah. Okay. Yep. Yep. So you flip the sign. What was it? 137, and that's a kilojoule per mole. Yeah, okay, I don't have a solution for this, but everything looks good to me. If we want to take this step one step further, they can ask you how much energy, how much energy is released or okay, this is terrible writing. Like this is lagging so bad. When it lags, the writing is really bad. How much energy? Yeah, I can't even write the much. Okay, well, anyways, so I'm just gonna say it. How much energy is released or absorbed when, let's say, they're gonna give you some kind of mass, like 2 grams of the C2H6 is reacted, or in this case, is decomposed, right? So you kind of need to do a stoichiometry. I don't think we need to go through that. Basically, you're going to turn the grams into moles and then multiply it by the 137, because this is saying for every 1 mole of the C2H6, you are producing 137 kilojoules of energy. That seems a little ridiculous, actually. So this might be a made-up question because those values are really high. Or maybe actually, yeah, this is a bomb. This is this can be a bomb. This is releasing a high amount of gas. I would say this could be done. How much energy is released or absorbed? Yeah. Okay. Do you have another question? Okay, so sometimes you might also see another type of question where you have to do Okay, this might not be like Hess's law, but I kind of categorize that as a Hess's law type question. But it has to do with heat of formation problem set. So stuff like this. So you could have an equation like this. All right. So this is the first question. I'm gonna copy that over. Okay, so this is another type of popular question. So I say these two questions are bread and butter for this. Okay, so this problem says use enthalpy of formation, and enthalpy of formation is basically saying this. Anything that's not in their elemental state. Let me move this guy down a bit first. So anything that's not in their elemental state. So for example, CH4, CH4, for them to put that together, there's some kind of energy that's needed to put these things together. O2, so something its own element found in their natural state. So something like a metal, for example, you got sodium. Sodium metals usually found in solid. Those usually have a heat of formation of 0. Okay, oxygen is found in gaseous form. It's a pure element, right? I mean, it is molecule with 2 oxygen, but if you only find only one type of element, and it's in the state that it's usually found in room temperature, and you don't really have to memorize this, just know the obvious ones, right? Know your Hofbrinkel gases, know your metal, right? So those generally have 0, so that's why when you look at so these values, usually you have to find it from the table, and that's what I was showing you earlier. I thought those were the questions we were going to do first. I was going to pull that up before you started pulling up this question. So you're going to find that in the back of the textbook as well, and some teachers give you a sheet to keep as well. So these are all the formations. So for example, the way to read this is ammonia, for example, it actually releases 46.19 kilojoules for every 1 mole of this being formed. So some of them are actually going to be absorbing heat, some of them are going to be releasing heat. Okay, so in this case, why don't I see a O2? Well, I just said that. It's because it's it's going to be 0 because it's in its own elemental state. So let's do part A. So part A, to do this, you need that equation I was talking about earlier. The delta H of the reaction can also calculate by, so we found one way of calculating already, and that's if we know the elementary steps. So right now I don't know the elementary steps. This is highly unlikely to be reacting all like once, because you never see 3 gas molecules coming together in the exact right orientation. That's just not as possible as 2 things coming at once. So notice most elementary step you saw earlier was 2 things coming together at most. Okay, 3 things coming together, generally that's pretty rare. Anyway, so we're going to sum all of the delta H values, multiplied by their coefficient. N stands for their coefficient, the mole in moles. So number of moles of them multiplied the delta H, because delta H is in joules per mole or kilojoules per mole of all the products. And then we're going to subtract it by sum of moles times the delta H values of all the reactants. Okay, so how this is done in practice is I'm going to equal to, so I'm going to do the product part first. So the product is I'm going to multiply 2 by, look at the chart. The chart says to form HCN, you need 130.5 kilojoules per mole. So I'm going to multiply 2, see 2, that's in moles. 2 moles, lagging. Here, do you want to try to write it? Yeah, you write it. So 2 moles. Yeah, so we, I don't. You can write units, or you don't have to write units. Up to you. Oh, there it is. Now it's showing me. I'm just gonna get you to write it. So if you just write the numbers, it'll be 2 times 130.5, and then we're gonna add that because there's summation. So what's the coefficient? It'll be 6, yeah, times negative. Perfect. Okay, I guess I overestimated how much we were gonna write in the bracket. Thought we were gonna write the units as well, but it's okay. So you can just see these are moles times kilojoules per mole, so you only have kilojoules left. Okay, and then 2 times. Yep, and then you just gotta punch them all into the calculator, and then that will give you the delta H value of the whole thing. What's the unit? Kilojoules, exactly. Okay, so just put that in, and then we're gonna do B. So I guess I kind of lied, but you know, these two are kind of similar. These two are actually pretty similar, but strictly speaking, there are 3 ways in this unit that they need you to learn how to calculate delta H. So we saw from the first one, we can add up the elementary steps, you know, provided that they cancel out to be your final equation. We see the second one where we can consult a what's called a heat of formation chart. So that's basically saying how much energy is required or is released when you put together these products, minus how much it gets released or absorbed when you put together the product, and that'll be the delta H value. So now looking at the last way now, B is saying, so B require you to know the Lewis structures of each of these, because this says still the same thing. B is going to be delta H of the reaction is going to be equals to the sum of all the bond energy, so still coefficient N, times this time bond energy, so bond energy of all the bonds. So this might take a while actually, product, depending on how big the molecule is. So I am gonna attempt this. So bond energy of the product minus sum of moles times bond energy of all the reactants. Okay, so this is quite similar as before, but look, we do need to write out the equation out in Lewis form, because I don't know how many double bonds, right? Because so this time we're using this chart here. It says to break apart NH bonds, you need 389 kilojoules per mole. So this is why we do products minus the reactants. So reactants, you're breaking the bonds, and then product, we're forming the bonds. Because one way of thinking about this equation is we got to break up all the bonds from the reactants and then rearrange them, put them back together. So that's why we need to draw the Lewis dot. We don't need to write out all the electrons, like especially the lone pair. We're mostly interested in what kind of bonds there are in each of these. So we have NH2, that's easy to write, right? NH2 is like that. Again, we don't really care about that lone pair there, but we know there's a lone pair. Methane, we know looks like this. And what else do we have? We have going to, oh no, one more. We have oxygen. Be careful, oxygen is the first tricky one, because oxygen we need to either remember it's a double bond, or we need to do the proper Lewis dot diagram, and you did that in like 2 chapters ago, I believe. HCN is another tricky one, but you know, if you follow the rules of, you know, do your electron accounting, put the central atom, put the peripheral atom, you would reason out that it will have a triple bond between the C and the N. And then water, we know how water looks like. That's not a tricky one. Okay, so looking at this, let's count up all the stuff. So, you know, some people just go right into the equation. That's what I like to do as well. But, you know, let's, just to be safe, let's count out how many of each thing each of these molecules have. So, for example, the NH3, oh, my thing is lagging again. NH3, right under it, I would write 3 times NH, because there's 3 NH bonds. And I'm going to be very careful, because I should probably put the coefficients here as well. So in each of them, so where's the coefficient? There's 2 of these, there's 2 of these, there's 3 of these, yeah, 2 of these, and 6 of these. So maybe I should actually write the total number. So because each molecule has 3 of those, so in total there's 6 of the NH bonds. So there's 6 NH bonds found in this, and that's about it. That's the only thing that's found in this one. The second molecule there with the methane, how many? What kind of bond do we have? And how many? Yeah, we have CH bonds. How many? Yeah, total. In total, because we have 2 methanes. 8. Yeah. So right now I'm kind of skipping over the n part then, right? If I'm counting these already, then I don't need to multiply by the n. Okay? But if you're counting, yeah, so I'm just going to put that, cuz that's how I like to do it. Or if you write 3, then you need to multiply by 2 after when you put into equation, right? If you write it like this, then you don't have to worry about that. Okay, for oxygen, well, 3 of those is just 3 oxygen bonds then. 3 oxygen double bonds. And that, we have a value for that, I believe. Yeah, we do. That's the 494 kilojoules per mole. And then what do we got? Oh, this one's a little tricky because we have 2 types of bonds here. So what do we have here for the cyanide? Yeah, 2C single bond H. Be careful, single bond and double bond can be totally different. So CH bond will be different depending on single bond, double bond. Right now we only see single bonds, but in other questions you might see more than that as well. Okay, so yes, so there's 2 CH bonds and also exactly, and then last one with the H2O. Yeah, 12 OH bonds. All right, so don't worry about breaking or not breaking. Okay, when you break bonds, generally it takes energy, so generally it's positive. And when you put bonds together, you generally release energy. But we don't have to worry about the sign. Whatever the table gives us, we need to just plug it into the equation. So sum of all the products. Okay, so we're going to basically do, for sum of all the products, we're going to do 2 times, so we're going to add all the product bonds. So CH was, here, you want to write this one? You can write this. I'll start you off with the first one. So we have 2 times, the CH ones are, and I'm not going to write in units, we're just going to remember that it's all kilojoules per mole. Actually, no, not kilojoules per mole, it'll be kilojoules because we multiplied the moles already. Right, we technically put the moles. That's 2 times, what do we got? C double bond 3, 879. Right, okay, yeah, my pen's not working. You can write it. Yeah. Well, yeah, 2 times, I'm doing the CH bond first, right? Oh, you don't need to 2 times 4. Where did you get the 4 from? No, because I already accounted for it, remember? Remember I said in there I already accounted. So in this new equation, I don't even put the n if we're doing this method. Because if not, then it should have been only 1 CH. Right? The 2 right here, I already accounted for that. Because look, if I don't consider the coefficient, how many CH bonds are there? There should only be one. So I already accounted the coefficient in there for the 2, right? Just like here, one molecule should only have 3 NHs, but I already multiplied the coefficient in there for that 2. So I have 6. Yo, if that confuses you, switch back to like the original way. So switch back to, yeah. Oh, okay. Oh, okay, I see, I see. Oh, you were seeing the CH. Okay, I see. Yeah, yeah. Yeah, so yeah, always, so this question and the last question, we're always doing product minus reactant. Yep, and then if you just put that on your calculator, then hopefully we will get, there's a certain number I'm looking for. Uh, 1014. Okay, well, it's a little bit off, but I don't see a mistake, so sometimes it might be. Because look, we calculated the exact same one as before. Last time we got negative 1213.4. So we're looking for a value that's close to that, right? Because these two are the same equation after all. So I'm just gonna look through this one more time, see if there's any mistakes that could have been made. 2 times, unless you made some calculator errors. Minus. Yeah, otherwise the steps are all there. And I realize I do have another student coming right up. So I know we started a bit late, so we did go over by a bit. So I will see you next week. Yeah, I guess we'll text each other for the time next week. All right, I will see you. All right. Alright, so that was a quick little tutor session, second half of a chemistry tutor session there, and I am going to sign off now, and I purposely muted the students' audio for privacy purposes. Alright, so see you later. Stick around, well, don't stick around, but come back maybe in an hour or 2. Or even more than that, and I'll be coming on to do some DJ or guitar and singing live. See ya.